Ticketing systems are a favorite system design interview topic because they compress many hard problems into one user action. Buy a seat. You need to survive traffic spikes, prevent overselling, keep the user experience fair, coordinate payment, and recover from retries. The core question is not how to draw a seat map. It is where inventory is allowed to change. Start with requirements. Users browse events and seat maps. At sale time, a flood of users tries to enter. A user can hold a seat for a short time, pay, and receive a ticket. The system must never sell the same seat twice. It should degrade gracefully under load, and every external side effect, especially payment and ticket issuance, must be safe to retry. The design also needs clear product policies. How long a hold lasts, whether seats are assigned or general admission, and whether fairness matters more than raw throughput. The waiting room protects the system before inventory is touched. Instead of letting every browser hammer the seat API, users enter a queue and receive signed admission tokens at a controlled rate. The waiting room does not guarantee a ticket. It guarantees that the core purchase path sees a rate it can actually handle. That token should be hard to forge, short-lived, and tied to the event so bypassing the queue is not easier than waiting. Inventory should have a single authority. For reserved seats, model each seat as a row with a state, available, held, sold, or blocked. For general admission, model counters but update them atomically. Caches can serve the public seat map, but the purchase decision must go through the authoritative store because stale cache reads are exactly how overselling starts. The user interface can be optimistic. The inventory right cannot. A hold is a temporary claim with an expiration time. The transition from available to held must be atomic, usually with a conditional update or a row lock inside a transaction. If the update affects one row, the user owns the hold. If it affects 0 rows, someone else got there first. A background sweeper releases expired holds, and the checkout page shows the countdown. This turns a race between users into one database decision instead of many application guesses. Payment is slower and less reliable than the database transaction, so do not keep the seat row locked while waiting for a card network. The usual pattern is two-phase at the application level. Hold the seat first, create a payment attempt with an idempotency key, then confirm the hold into a sold ticket only after payment succeeds. If payment fails or times out, the hold eventually expires. That keeps the scarce resource protected, without letting an external provider freeze your inventory indefinitely. Retries are unavoidable. The user double-clicks, the mobile network drops, the payment provider retries a webhook, or a worker crashes. Every mutating command needs a stable request id store that id with the resulting order or ticket. If the same request arrives again, return the same result instead of creating a second order. This is not optional in a ticketing system. Payment providers use the same idea because network retries are normal, not exceptional. Ticket issuance, email, analytics, and webhooks should follow the database commit. A transactional outbox is a clean pattern. In the same transaction that marks the seat sold, insert an event into an outbox table. A worker publishes that event later. If the worker crashes, the row is still there. If it retries, consumers use event ids to deduplicate. This avoids the classic bug where the database commits but the email, webhook, or ticket PDF silently disappears. Scale the red path and the right path differently. Event pages and seat maps can be cached and replicated. The purchase path should be narrow, partitioned by event or venue, and protected by rate limits. Hot events may need per-event queues, regional routing, and capacity planning. But do not shard away the invariant. One seat can be sold once. If a seat row can be written by 2 shards at once, the architecture is faster only until sale time begins. A strong ticketing design is a state machine around inventory. Waiting room controls demand. The authoritative store owns seat state. Holds are atomic and expire. Payment is coordinated with idempotency. Sold tickets emit events through an outbox. Reads scale broadly, writes serialize where correctness demands it. That is the difference between a checkout page and a real ticketing system.